Greetings gang, welcome to your Chapter 25 lecture video. Most of Chapter 5 can be summed up in a single statement, and that is Faraday's Law. Faraday's Law, put simply, is that nature abhors, detests, absolutely loathes a change in magnetic flux. Magnetic flux is defined to be the amount of magnetic field that goes through a certain area. Now imagine you have a loop of wire, and inside this loop of wire there's a magnetic field directed into the board. Okay? The loop of wire has a certain amount of area, and so there's a certain amount of magnetic flux going through the loop. Now if we reduce the amount of magnetic flux through the loop, say by reducing the strength of the magnetic field, what would happen is the electrons that are in this wire, in this circuit, would move around the loop in order to generate a current, which then in turn would generate a magnetic field in the opposite direction of the change in magnetic field, or, put more simply, would make a magnetic field in the same direction as the old magnetic field in order to try to restore the magnetic field's strength as the magnetic field got weaker. Now, according to the right-hand rule, the electrons would generate a current in the counterclockwise direction, like so. Because, according to the right-hand rule, a current gets created this way, and a magnetic field would wrap around it like your fingers if your thumb is in the direction of the current. And that's actually going to make a magnetic field pointed into the board opposite the direction of the magnetic flux. But this actually means that there are electrons moving that way, right, clockwise around the loop. Because again, our goofy definition of current is stupid. Now, we usually write this expression, Faraday's Law, as the EMF, or the electromotive force, the voltage in the circuit, whatever you want to call it, is minus, because it's in the opposite direction of the change of magnetic flux, equal to the partial derivative. I know we're using some sophisticated math terminology here. But it's equal to, essentially, the change in magnetic flux with respect to time. And the minus sign is there to show that the current is going to be generated in the opposite sense of the change in magnetic flux in order to try to restore that magnetic field. Now, I know it's funny to think, because it's something that's not exactly intuitive, right? This is not something that you can see very easily. But it is absolutely true. And were it not the case, we wouldn't have any electric generators, and anything and everything that we use with electric power wouldn't be on right now. You probably wouldn't be watching this on your computer or on your phone. Now, the electric generators that we use to make power are built upon this principle, and this is also how we generate AC power. Imagine now we have this loop inside a magnetic field, and it's able to rotate, right? And as it rotates, the amount of magnetic flux going through the loop is going to change. So we've got a certain amount of magnetic field going through this loop, and as it rotates, so it's 90 degrees from where it was, now it has no magnetic field going through it, right? And as it goes this way, and as it turns around, then it's going to have magnetic flux going through the loop the opposite way, right? And what that's going to do, it's going to generate a change in magnetic flux one way and then the other way, and it's going to oscillate back and forth, generating an AC signal or an AC voltage. So that's how we generate AC power. Usually, we boil water and use the steam to turn a turbine, or use a river or something along those lines in order to try to turn the wire for us, and we turn some mechanical work into electrical energy. Now, if you recall, I mentioned in chapter 24 that changing electric fields create magnetic fields, those things that we called electromagnets, and now we can see that changing electric fields, or excuse me, changing magnetic fields, like in a loop, will generate electric fields or currents, and that's called Faraday's law. As a matter of fact, Faraday's law is basically one of 4 equations called Maxwell's equations that govern electricity and magnetism. Now, you don't have to know these because the math in them is actually far above and beyond this course, and so I'm not going to get into what all of this actually means as far as the math is concerned. This is the divergence of the electric field. It's basically, you know, how the electric field moves through space and time. This is current density, and so what this equation says is that one of the sources of an electric field is charges. That's what it really means. There's this one, the curl of the electric field is equal to the negative time derivative, or the change of the magnetic field. This here, this expression is the curl of the electric field. And it has implications as far as the geometry of the electric field. Now, what this equation means is that a changing magnetic field can generate an electric field. That's Faraday's law. The third one of these equations is the divergence of the magnetic field is equal to 0, and what this means is there are no magnetic monopoles. Then that means that every magnet has a north end and a south end. You can't have one that just has a north end. It doesn't work that way. If you broke this magnet in half, you would have a north end here and a south end here, and this one would become a north end here and a south end there. There are no such thing as magnetic monopoles. Now the last one, the curl of the magnetic field is equal to permeability of free space times the volume current, right? This is a current, plus the permeability of free space times the permittivity of free space times the change, or the time derivative, of the electric field. Now what this means is the source for the magnetic field is currents, or changing electric fields, which are really kind of the same thing, right? So, the sources of electric fields are charges and changing magnetic fields. And the magnetic fields have the source of magnetic fields, is currents, like in a magnet, the eddy currents or the circular currents, the domain currents, whatever you want to call them, and changing electric fields. Now, I know you want to see some evidence, some proof of this Faraday's law stuff, just so you can believe in it. So I want to show you this. This is a magnetic flashlight. You can see that there's a magnet inside it, right? You see it sliding back and forth. And there's a bunch of copper wire here. Now, as the magnet slides back and forth, the magnetic flux in the copper wire is going to change. And it can make light. And if I just charge it up here for a second, like a shake weight. You guys remember those? So if Faraday's law wasn't true, if you couldn't get an electric field from a changing magnetic field, this would not work. So electricity and magnetism electricity and magnetism, are related inextricably. Where you find one, you will always find the other. In any case, now that we understand Faraday's law, and we're all brilliant magneticians and physicists, I want to delve a little deeper into the workings of a device that we've already sort of hinted at, this thing we call a transformer. And no, I'm not talking about Optimus Prime. And by the way, if you like the Michael Bay movies, you're just a bad person. In any case, a transformer is essentially like a magnetic core or coil or something, like an iron bar with a bunch of wire wrapped around it. Now, as current flows through this coil, what is going to happen? Well, it's going to create a magnetic field, right? According to the right-hand rule, as the current goes through the wire, it's going to create a magnetic field. And that's going to carry itself through this iron bar, right? This core. Now, typically, a transformer has two sets of wires, right? One of these will have like a certain amount of turns, and this other one will have a different amount of turns. So as current flows through one of the coils, it creates a magnetic field in the core, which induces a current in the other wire. Now, the amount of voltage that's in these wires is going to depend on the amount of turns in the wire. Also, if you try to apply a DC current to this first wire, it's not going to change the magnetic flux inside the core, and that is not going to change the magnetic flux inside this wire and make it generate a current. So this only works with AC, right, with our alternating current signal. Now, let's say that this has a voltage of 10 volts, and this has 100 turns of wire. Okay? If this has 200 turns, that's twice as many turns of wire. That means it's going to be twice as magnetically susceptible, and Faraday's law is going to generate twice as much voltage, right? So the voltage here should be 20 volts. So we feed in 10 volts here, and we get 20 volts out. This is what we call a step-up transformer, and this is like what you have at power stations. Because power lines have really high voltages. But wait a minute. It seems then like we're violating the law of conservation of energy, right? Didn't we just take a certain amount of energy and get a different amount of energy out? I know it may seem like that, but it actually becomes really obvious if we think of this in terms of power. Now I'm going to assert that power, because power is energy per unit time, right? And presumably, if the energy per unit time is going to stay the same in between 2 points, then energy is going to remain conserved, right? Because obviously time is going to be invariant in both of these locations, right? Okay. Now if you remember, we had a definition for power, for electric power, and that was current times voltage. So we're going to have a certain amount of current here and a certain amount of voltage. And so if we have double the current, that means we have to have, if we're going to have double the amount of voltage coming out, that means we have to have half the amount of current. And this is why over these power lines, we want to have a lower current, right? We want to have less electrons actually moving, because that takes energy to move them. And unless you have a superconducting wire, you're going to have a greater energy loss with more current than you're going to have with a higher voltage, right? Thus, we can very plainly see that if, let's say we had, I don't know, a current here of 10 amps, right? The current here would have to be 5 amps in order for energy to remain conserved. But the punchline is, I wrote a T on the 1 because I'm thinking the number 10. But the punchline is that energy has to remain conserved, right? Even though we're using a transformer, we can't just magically conjure a bunch of free energy, right? In any case, I hope you have enjoyed your lecture video for Chapter 25. I'll see you again soon.